last day of lectures, last lectures. So today it's going to be a little different from yesterday. So it's going to be a bit research-ish kind of focused, but we'll start slow. And I think we will start with one thing that we kind of had from yesterday, which was this scheme here, right? I didn't really talk about any scheme, but just kind of how would you make entanglement in this way? And I was hoping that you had a chance to think a bit about it, and if there's someone that could come up with an idea, what would you use to make entanglement here? Kind of what would be the success probability? What was the fidelity? You don't need to come up, you can just sit and talk, don't worry. There are many ways of doing it, so. Oh, okay, no, all right. Okay, so the photon pair source will probably be an SPDC source, so at least one thing that we know is that there will be a fundamental rate fidelity trade-off, right? That with some probability you'll get a photon pair, with some small probability you get more than a photon pair, so that will definitely be a limitation of this. Then we need those photons that are entangled, they need to interact with the spins. How can we do that? There are at least two options from what we discussed yesterday. Which scheme are you going for there? It's 50-50 chance you get it right. Amplitude? Yeah. Yeah, so in amplitude we would start with a 50-50 superposition. So indeed you could start with a 50-50 superposition of both spins, these photons here. What kind of encoding would we use for the photons? The photonic qubits, that means. Yeah, that would be naturally fitting for the scheme we discussed yesterday, indeed. And probably also we don't want to use polarization because it's difficult to send over distance and whatnot. So yeah, time pin could definitely be one. We could do the amplitude-based. So forgetting about the inefficiency of the source itself, what would be successful if you use the amplitude-based? And how would you arrive at that? Yeah. So okay, we know that the amplitude-based is 50% successfulity at least, right? And okay, 50 on both pairs, that's a quarter, yes. There's also this annoying thing to do detection. And all right, if we have an optical switch, then yes, we would get the 1/4. If we do not, then we'll have another 50% from the detection on both sides, right? So 160, yep. And we could, of course, improve it if we used maybe the phase-based instead, but that's just, we need to get some fat people to make that work, basically. All right. Yes, so that's that was one how to do that. All right, I'm sorry, we're going to start with basically you guys doing all the work. And it's because today's topic is a bit applications of quantum networks. And unfortunately, well, I'm single two types of applications. There are definitely more, but not that much more. So I think I counted you were about 30-something people. And actually what I would like to do is to put you into groups where you need to discuss with each other. The task you can read here. And I think the best way to do this is probably that I'm just going to, give you some numbers, and those numbers are saved together. And we'll probably, say, take, what do you need, 15, 20 minutes? 15 minutes, let's say 15 minutes for the groups after you go to discuss and come up with these things here. And yeah, please make sure that one of you take notes during your discussion. please make sure that you already in the beginning select someone that's going to basically present your stuff on the very nice whiteboard here. And presenting means basically, of course, which of these applications did you choose and why? Maybe you all choose the same, we'll see. So I'll just get through. So I think let's do maybe, should I count to 6? Maybe let's try that. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Are we at 6? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Wow. 1 and 2 over there in the corner if you're participating. All right. So, feel free to leave the room. You don't need to also sit in here. 15 minutes. So let's let's give it a bit more. So let's say we reconvene at 9:30, and be prepared that your presenter can come up and say something here. All right, and of course, indeed, this little cartoon is put there for a reason. We're trying to figure out kind of what matters and what does not matter for these quantum networks, right? All right, so please go together in groups, go ask it what you want to do, discuss, come up with what are the most promising applications for these distances, and come back 9:30. So remember that one of the motivations that were highlighted yesterday was money. So let's see if we can also find some applications here that will make those money for those that were motivated by that. I don't know. But yeah, so I'm very curious to hear what you came up with. I think we're just gonna start with group 1. So who's the presenter from group 1? Great. Do you need a mic or can you shout?
Can people hear me okay? Yeah. Okay, so did you want 2 for each or just 2 in total?
2 for each, but it can be the same. And if you could maybe write on the whiteboard what those applications are. So maybe like a small scale, metropolitan scale, large scale.
Okay, so for the small scale, I guess like fully networked like quantum computing, so like some quantum data centers. So it's kind of what companies like Quantum are doing, where they can only fit a certain number of sources, or maybe supplemental computers that can only fit a certain number of qubits inside of a processor. But then to be able to do a useful quantum computation, you need qubits or large systems. So one way to do that is to network qubit systems together.
So to scale quantum computers, basically.
Yeah. So
and by the way, feel free to ask questions to the presenter, right?
You need to be able to distribute independent states fully between these things to do stuff.
If you didn't come up with 2, it's also fine.
So, okay, well, that's fine. And then, like metropolitan scale, on the topic of quantum computing, you could do like blind quantum computing, which isn't quite as intensive as doing like fully distributed quantum computing in a sense, where you maybe just send some like state into a quantum computer that works. Some other company owns, but maybe the computation you want to do has some like proprietary information. So I think what we were discussing, like you can put some Go phase on, and you know what that is, and they don't know. So say if I'm getting all overlaps and wanted to like work out what you were doing, they couldn't, because they wouldn't know the space, so they could just count the information down, and they could have done the step that final back to you. And you could decode it with your phase, and then there's another sort of metropolitan one would be and then a large scale one that talking about was a.
Oh, please don't erase it. All right, okay, we have networked quantum computing in small scale and BQC blind quantum computing in metropolitan scale. Okay, let's just leave it at that.
Okay, and follow up the large scale is distributed quantum sensing, and in particular, if you go to that, I'm going to say talk on distributed scale is a piece of cost proposal to do like LBI, so like that's like sort of like not like large scale like telescopes. Maybe you don't have the image of black hole like telescopes might be a image. And it turns out with like you can get slight resolution advantage. And then I don't actually fully remember how it works, but there's a proposal where you have two telescopes, distance larger then you have several air sources, and they these two telescopes and with operation. You can get some extract voltage information from the appearance crystal that are in space. You can get a resolution image.
Awesome, thank you. Any questions? Here, stay. All right, thanks. I'm just gonna clean this up a little bit, and then meanwhile, group 2 should maybe center there. And okay, so small scale network QC, metropolitan scale BQC QKD, large scale telescope arrays. Yeah, that's all right, great. Group 2. Awesome, and if you could kind of write the application here and then use that part for explaining if you want it. And if it's the same, just do it.
So for small, can you hear me? Yes. So for small scale, we thought more security applications. For example, if you want to transfer sensitive information, for example, from banks or companies or healthcare or military development, one is within the same place. Small scale, we thought about secure application, but also scale. But then you have the problem of delay and the speed is lower. It's difficult to deal with, but for example, the secure environment, so for small scale, we talk about good security, secure.
But it's beyond QKD is what you're saying, or?
Yeah. Sure. Scale model the speed also focus. And for one that we thought about all scales maybe DQC because you could, for example, use to connecting different processors to the same computer or different computers in the network or different networks. Think about the internet, for example. So I put DQC everyone agrees in every scale.
Okay, and I guess DQC is the same as network QC, yeah? Yeah, okay. So just, yeah, DQC, let's call it that. Did you discuss what was the application for DQC at metropolitan scale and large scale? Kind of why do you want to link the computers together?
So one thing that we discussed is that for example, small scale have say limitations on the connectivity. Maybe let's say from this limitations of that connectivity, so you can connect to other computers or processors in different places that you are. So you know, let's say for this local limitation on. But then you have some problems, for example, if you have different images that are fun to do with the interface.
Okay, so it's that there might be specialized quantum computers, so to speak, that you have one hardware that's good for something, but you want to link to another hardware that's good for something else. Is that the?
Yeah, they could also do similar things, but they interact with them for the sustain programs.
Right.
For a larger scale, we've also got
Okay. Questions? No, thanks so much. Yeah, we can clap if you want. For the group 1 presenter, sorry about that. Let's give a round of applause for group 1 presenter as well. All right, group 3. It's okay to say what he said, but you know.
Well, for the small scale, I think you have something different. We just thought that we can use quantum sensing in everything that we have already. For example, we were discussing about OSP, like that's later. If you use every single tool that you have to improve, so let's say you can improve SSPDs, that would like to be good. So basically, you can make your solution, but at least one tool, right? So we can improve our safety tools in a small scale.
And you mentioned a concrete one, you said, right? Spectral analyzer, or what was?
Yeah. Well, otherwise, it's just a great checks the amount of light in each wave, right? So you have quantum sensor there, you're getting better resolution.
Okay, yeah. I mean, please put the concrete one on there. So yeah, the concrete one that you mentioned. Yes.
Yeah, basically anything that you can do with quantum, you can just put it in whatever you just like already. We also have distributed quantum computing, so here error correction, like you're gonna do the small scale error correction. So yeah.
But how does quantum networking come in as for quantum networking?
Networking is more about the relation of allocation, right? So maybe you can just have an allocation that does error correction, your small scale, and then you use the measurement.
Sorry, can you try and explain again? So you're saying quantum error correction is on the networking level, or you're saying that there's some quantum error correction that you connect to with the quantum network, or what is the?
Yeah. You want to play that?
I see. Okay, so it's the quantum network is linking these two modalities together. Is it different from DQC then, or? Okay, yeah. Okay, so what do you want to call it? The application? Distributed error correction. Okay.
For the mid-range, the competence scale, we had these two.
So you had which two? PQC and
One for the computing and one to get to the rotation scale.
I see. Okay, so DQC and PQC. Yeah.
For the large scale, we started trading it. So we have UAV development. Like for example, or other protocols for satellite. We have quantum science application, like basic science. We can start doing quantum gravity in the large scale.
Okay.
Basic science of gravity.
So tests of gravity, basically. Quantum gravity.
Well, we talked about mapping the SH game to different applications like server load distribution and high frequency trading.
Okay. Quantum coordination, I guess. But you're only supposed to choose two. And you have okay, you picked those two. Okay, great. Then that'd be the all right. Questions?
Well, LIGO is so you can do that and stays in the and you can just not sensitive that. We say they already in such a way that this is way harder.
All right. Thank you. Moving on to group 4.
Hello. So I guess I know inside that work. Quantum computation myself, it's technology for applications, not the usual. I'm not able to do it. Also, we wrote down quantum machine learning. I don't want to do quantum machine learning. We discussed about it.
So could you specify where the networking, I mean, you're saying that the networking is to enable the quantum computer that can run quantum machine learning, is that?
That's true.
Okay.
So this quantum machine learning actually is more like federated learning. So if you distribute or partition these quantum machine learning circuits, and you can you have a metropolitan or even large scale network, so you can do use this for federated learning where the data is secure because it cannot be cloned, and you can actually run your machine learning algorithm on different processors and then synchronize them. So it's actually distributed federated learning.
Okay, so it's like distributed quantum machine learning, and it's also distributed secure quantum machine learning. Okay, yeah. And it sounded like it was both small scale and metropolitan scale, or?
Metropolitan scale and large scale.
Metropolitan scale and large scale. Okay, yeah. What should we put on there then? Maybe it's kind of like a subgroup of DQC, right? So could one say DQC and then a little kind of example, distributed secure quantum machine learning? Clock synchronization, I guess, yeah. There might be, maybe you want to use a different pen. It's a little. So, what was your motivation for putting that on metropolitan scale? The clock synchronization? Yeah.
I mean, if you are like below 100 meters, again, yeah, but like you did ask before. I think it goes everywhere. But that's why I would get to the site before. So, yeah, you're raising it.
Yeah, there was maybe a comment or.
Also, as box use small scale,
Okay, so right. Okay, so it's kind of a little bit of a compromise that is in metropolitan scale because you kind of saw it in both small scale, metropolitan scale, and maybe even large. Okay. Mm-hmm.
Then for large scale, again, very good as a down public sensing methodology, as a part of this category. And then also organic methodology, I guess.
Okay.
So yeah, public sensing very
Mm-hmm.
yeah, that's it.
Yeah. Questions? Comments? All right, then thanks. Group 5.
So for small scale, we were everybody agrees that computing was the most applications. Line quantum computing. So node linking to make a cluster of several
Sorry, it's a cluster? Is that what you're? Oh.
yeah.
But it's kind of like, it's the same as network QC, no? Or.
Oh, yes.
But you said you also put BQC on the small scale?
Yes.
Okay. Yeah.
So for the metropolitan scale, so it was mostly for quantum sensing application. But this one can be also put in large scale.
Mm-hmm.
So, for example, one application that was not discussed, maybe trying to work on earthquake detection or from measuring the vibration in a certain area, because we need quite precise sensor.
Mm-hmm.
And that means if we connect them together, we can have a very sensitive detection on a large scale. So maybe by trying to find some relation between different sensors, we can manage to have a very good sensing capacity. So I think.
And sorry, what was it that you wanted to sense?
So there is some application for astronomical detection and also I think for earthquake detection or for vibration or infrastructure.
Okay, so astronomy, is that the telescope array, I guess? And the other vibration you said was like vibrations across a city, or what was the vibration?
So my idea is that maybe if we have different detectors,
mm-hmm.
Accelerometer together, maybe it's possible to create some
very interesting. I think I'm just trying to get like the specific what you would sense with it, with this more sensitive distributed earthquake. Oh, I see. Okay, so earthquake detection, and I see.
Yeah, because it's mostly
Mm-hmm.
100 kilometers, not program. And for large scale applications, so one application that was not discussed is I don't know really quantum identification. May be useful when we want to vote of administrative tasks to kind of prove your identity. And someone mentioned using it coupled with some kind of GPS to track. So for
So it was
internet security.
yeah, position verification. Was that what you or?
Yeah, basically identification.
Yeah. Okay. Authentication or identification? Okay. Yes. Secure identification. Let's put that there. And I think.
And also there is also another application of GPT and networking application that's kind of related.
Mm-hmm.
Yeah, for the rest of the all systems.
Yeah. Thanks. Yeah. Okay. Last group, group 6. Yeah. Yep.
So, don't really have much to add. I got stuck. We were discussing on the promising thing.
Well, that's actually kind of interesting. So what was the discussion about in terms of promising?
Well, where are we going? Why are we doing this? We kind of got a little bit more deep than it should have been. In the end, we kind of settled on small scale and longer scale applications like network quantum computing because of our parent ability of building some large machine that can work on itself. And also we're discussing remote sensing. Well, that was also very discussion about remote sensing on device or in large metropolitan areas. Some were about the idea of because detecting terahertz radiation will be members of terahertz radiation from the area. And also clock synchronization. That seemed like a thing, but then because of the promising stuff, we decided to move away from the quantum money and decided to say that, well, it was promising to us for less fundamental physics. So quantum gravity is one thing that we were discussing and we'll actually discuss quantum gravity. That's
All right. Questions? Comments? Then thank you. Okay, thank you all very much for really taking this serious and coming up with all these applications. Maybe so one thing that's kind of interesting, I think, is that down here we have QKD, DQC, but also a lot on kind of fundamental things like telescopes and gravity, so on. So that's kind of new physics, I guess. This is it, right? Small scale, quite a few people mentioned network QC or DQC here. Distributed error correction is kind of they're kind of related, I would say. I mean, they're different, I get that, but a little bit related. DQC, I would like to ask kind of, so this is a list of all sorts of different, some are more speculative than others, I would say, right? I mean, quantum gravity, we don't know. It would be cool to find out, sure, but it's definitely speculative. Maybe a little bit kind of like the discussion that the last group had of promising. What does it actually mean for this to be promising? Because there are a lot of applications here that are interesting, definitely, and so on. If you were to take this list and now start to think about, okay, which of these are the most promising? what would be your criteria actually to make, what makes a promising application?
Feasibility,
Sorry?
actually like build the system that can reliably do it.
So feasibility, can you actually do it? Is one thing. Yeah. So basically, I guess that's the same as saying, okay, is the hardware mature to do these kind of things? Is it something we can do near term or not? Right? Kind of feasibility. Okay. So feasibility is one. Let's see. Promising usability. Practicality maybe. Scalability, someone mentioned. Scalability, could you elaborate on why that is, for whether it's promising? So meaning that there are many, so I guess I'm after whether it's a technological scalability that you can build the system big, or whether it's scalability that is something can roll out to many users or something like that. Both, okay. Scale hardware. Scale user base, to use that word. Okay. I'm sorry? Usefulness. Usefulness, yes. What does that mean?
It's useful.
Sorry?
If it's applicable to the government, it's like the finance industry. There's a market.
Market, okay, money, yeah, okay. Market case, well, yeah, market case. Will people pay? Yep.
Kind of relate to that, if you have like a classical way of doing it, yes, worse, but like still kind of, you can still do earthquake detection, not necessarily as well as numbers, but like if the amount of technology you need to develop before you get the small game,
Is the advantage worth it? All right. Of course, people have different ideas. I think like this last one is one that I care very much about. Is the quantum advantage really worth it? Because there are many cases where we can say, yes, you might be able to improve it by something, but in practice, do we really care? I think another one that also people indeed care about, actually, it doesn't matter if people want to pay for it, just do it. That can also be one from the business case, that even though you could say from a quantum physics perspective, look, you're not gaining too much, but if people are excited about it and wants to pay for it, then maybe you want to do it, at least if you want to make money, that I know some of you want to. But yeah, I invite you definitely, this is really, to, check these kind of feasibility criteria or promising criteria, and think about which of these applications that are listed here, the things that you're going to also in this rest of this lecture, but also kind of moving forward, kind of things when you go to conferences and whatnot, and people talk about applications. Keep these in mind, like ask the question, is it really worth it? Is this a real use case, or is this just kind of interesting, physics? Could also be nice, I mean, definitely. But I think if you want to motivate this beyond just researchers, it's very good to keep these things in mind. Okay, I think we're, oh yeah.
You heard our opinion, what's your opinion?
Yeah. Yeah, my opinion is I think for small scale network QC or DQC, definitely, I think it's something that we do need to scale quantum computers. I think a modular approach is, sorry about this. It's something we need to scale it up. I think, I mean, we can also go for a monolithic architecture, but I think it has some engineering challenges. So I think, yes, we probably need to modularize. I think that's one of the most promising in here. This is really bad. Yeah, should I take the mic instead? Or, yeah. Let's see. Yep. Okay. Right. So small scale, I definitely say DQC. I think also, I'm not sure I'm saying this in particular, but I do think that there are some things where we basically transduce sensing signals to, for example, quantum processors, and these kind of things could be very interesting on the small scale. I think it falls within this, but I'll talk more about that in the lecture too. Metropolitan scale, I think DQC for sure. I think it's something where that could be something we're seeing, right? I mean, there are quantum machines on that you can access through the cloud. So doing that securely, I think, is something that indeed people might care about. I know that government people might care about these things. QKD as well. I mean, we see a market for it. There are definitely people buying QKD on the metropolitan scale. So I would say these two here. On the large scale, I think I also agree with QKD. Because if there's a cheap way to have QKD on large scale, it also seems like people actually are interested in it and want to pay for that. So that's a promising one. And I think synchronization down here, kind of these fundamental tests, let's group all this like quantum gravity and whatnot, I think also are promising. That's something that we've seen kind of in the past, like LIGO is a big scale kind of fundamental testings, right? And CERN is the same thing. If it would be very interesting, we can use quantum networks to make a new kind of fundamental test of nature there. So that would be my 2 cents on this. But it might be different in a month from now. I don't know. But, all right. I think what we're going to talk about next is blind quantum computing as one of these applications. One of the most promising on the metropolitan scale. Yeah, that's why I chose this one. And what I hope that we will get from this part of the lecture is that we can understand and evaluate the requirements for fault-tolerant blind computing, and also discuss kind of, what are the different levels of security that you might want for blind quantum computing, and also the practical trade-offs of that. And let me see, in principle, I think we should have a break before we start with this, because we've been going on for more than an hour now. So before we dive into blind quantum computing, maybe take 10 minutes. So let's reconvene 10:20. Get your mind off applications and more towards the thing. Okay, take 10. Okay, I think we're gonna slowly start in the interest of time. Okay, so PQC, I guess what is kind of the main primitive, it is that we should allow remote users to access a quantum computer without reading sensitive information about input data, the algorithm, or the results of the computation, right? And the main kind of motivation is, well, there might be some evil company, AWS or whoever that has this quantum computer, and you want to buy and develop your new drug on it or something like that. You're afraid that you might, spill some sensitive information to them, so that they go and patent it before you or something like that. And basically, there are two high-level hardware requirements for PQC, right? You need a quantum computer, and you also need that quantum computer to have a network interface, right? So you have to be able to link it to a quantum network. Something that, for example, is a bit difficult for superconducting qubits. You need to solve the transduction problem there, going from microwave to optical. Other hardware like atoms or ions, then naturally have an optical interface, for example, for these things. So yeah, you need to keep that in mind. And then another thing is that you need to be able to basically transfer quantum information, at least if you want the highest level of security, to your user. So you need to have entanglement distribution over a network. Right? So that's where the quantum network comes in. Right, let's see. Okay, so let's just start with first kind of make sure that we are all on the same page on what does it mean to do blind quantum computing, and where does the idea come from. And probably I expect some of you already know. I know that some of you already know, but there's a kind of very fundamental link between blind quantum computing and measurement-based quantum computing, right? And measurement quantum computing is where you kind of create a big entangled state and then do measurements to do your computation. And what is very useful is to think about this notion that we can have a universal gate set, meaning that we can basically decompose any unitary that we want to run on our quantum computer here into just a sequence of these elementary gates, right? And that can be, for example, arbitrary single qubit rotations and a control phase gate. It can be single qubit rotations of this form, which is basically, you can think of like a combination of a Hadamard and a phase gate on a qubit. If I can do this for any kind of phase here, then I can do any kind of single qubit rotation. And you know, the CZ gate is like this. So if I have access to this, I can do whatever I want. Almost. Okay, so to kind of understand measurement-based quantum computing, I think it's good to consider just a bell pair. And the notation that people use here is that you want to, write these entangled states that you use for measurement in quantum computing as cluster states or graph states. So you can depict them. There, a node is kind of like a qubit prepared in an equal superposition, 0 plus 1. And when you do an edge between these qubits, it means that you do a controlled phase gate between them. So a bell pair like we have here is basically that two nodes connected by an edge. All right? So what happens if I measure the left qubit in a basis consisting of this? More specifically, do like this. And my question is, oops, what is the output state of that qubit if I do this measurement? And I would like you to answer that question. Is that a hand or? Nope. Okay. Anyone? Can you please write on the whiteboard maybe what the outcome state will be? Yeah, thanks. plus minus e to the I theta minus. Yeah. Do people agree? I take that as a yes. Yeah, and the plus minus depends on which measurement outcome you get, right? Yeah, okay. Now, I would argue that the state that you've written there, oops, is actually this state, which I don't think is correct. Is there a reason why it's not correct? I would argue you need that one there. I might be mistaken, but yeah. Can I take like complete silence as I'm not sure whether you're agreeing or whether you're disagreeing, so please speak up. Yeah. All right, yeah. Any other problems? Or are we getting there?
Open plus and minus pairs in the 0, 1 basis. They will add that. So then
yeah, sorry, you're talking about the normalization constant, or? Yeah, so I mean, these two are orthogonal, right? Plus and minus.
when you open them in the 0, 1 basis.
Yes, there will be 1/2, and then there will be something else. Yeah.
So yeah, 1 plus e exponential and 1 minus f. So that
Yeah, I mean, but I mean, it's probably normalized this state, right?
plus minus basis.
If you open it up, you would get 1/2, and then you would get 1 plus e to the minus I phi 0, plus minus, no, sorry, plus minus here, and you would have plus 1 minus plus e to the minus I phi 1, which is also normalized. So yeah, I think we have the right state. Okay, good. So now we've done a single qubit measurement and we have the output state. I hope I can convince you that this is actually the same state as what we've written over here. I just apply this single qubit notation, and this X here, this is a Pauli matrix X. So, you flip the qubits depending on the outcome S, where S here is either 0 or 1, 0 being that you've got outcome 0 plus, 1 being that you got the outcome 0 minus. So if you define S in that way, then I can write this output state in that way. All right. In general, if I start with a qubit in some arbitrary state psi, and I do this entangling operation with one of these qubits in the equal superposition, and I do this measurement, I will get this state afterward. And I invite yourself to check that. You basically just need to do the same calculation that you did now, just with a different starting state. Okay. So what happens if I make such a cluster state here, where I now take and measure both the two left qubits here, one in the basis theta 1, one in the basis theta 2, and please note that this is the effect. I don't sit and write this out explicitly. What will be the state? You are allowed to express it as basically some gate acting on a qubit. What will be the output state if I measure these two? So what I'm after is, could you write sort of like an expression like this, but now there will be more gates in front. If I do this measurement. Exactly. I'm just doing this again and again, right? Because you can use the fact that just told you it doesn't matter what the input state is, I'll get these gates acting on it, right? So I can just apply this first time and a second time, and I'll just have these gates applied in this way. All right. Now, if I now want to implement exactly this operation, theta2, theta1 on a plus state, up to a final Pauli correction. So that means basically that I want the state to be expressed in this form. I can do some Pauli, whatever. That could even be C here, some other. And then I want theta2, theta1 on plus. So this is what I want out. This means that I just have a Pauli correction, which basically just means that I'm updating my Pauli frame, right? I mean, so what a Pauli operation does is it can flip 0 and 1, or I can also just redefine what 0 and 1 is, right? I don't need to physically flip them. I just call one 0 and the other one 1. And we have the C operator also, well, it just flips the phase. So again, these are not things that I need to physically implement. I just need to kind of keep it in mind such that at the end of the day, I just redefine what I call 0, what I would call 1, what the phase is. That's what I mean by just updating the Pauli frame of what I'm doing, right? So kind of like classical. I can interpret my measurement results that I'm doing on the cube afterwards differently than before. So useful inequalities is this. And again, feel free to check them, especially writing down, but otherwise take them for granted. And my question is now, I hope I didn't give the answer here. Yes. How should I choose my measurement basis? So remember, I do measurements in bases like this. Remember, this is the effect of these. But how should I choose my measurement basis to ensure that what I get out in the end is this thing? So I'm looking for basically I have measure in X, measure in Y. And I want you guys to figure out what is X and Y to make sure that I get this operation.
Like state one, last state
Please write what the X and Y is. Then I'll just take another one.
So S1 is either 1 or 0.
Yes.
0.
That's right. So
you should like upload that. So
you need to take into account the measurement of the first one. Exactly.
yes. So this. So 0. Okay. So but here it should be -1 should be +1.
+1.
I have a +1 there.
Because you measure.
You want to have minus in case. Yes, exactly.
So you should pick this. So X is.
No, just the fact that if you didn't have any correction, you would want to measure in minus θ1. So if S, so you just need to.
So X is minus θ1.
Yep.
Minus.
I think I would put a +1 here, because let's say that you didn't need a correction, you would need to measure in minus θ2, right?
Yeah, that's what it. So
So,
minus this is.
oh, you have a minus. Okay.
Yeah.
I see. Yep. Yeah, exactly. Nice, thanks. Indeed, so what we're seeing is, okay, I can deterministically kind of implement this operation on this qubit by doing my measurements. I do need to keep things in mind, maybe actually that I need to adaptively choose my measurement basis based on the outcome from before, right? So based on the first measurement, I need to update the next one, but in that way, I can ensure that I end up with the state that I want in the end, up to some kind of known Pauli correction. So I end up with this thing. So that's my Pauli correction. Okay. And that is basically what you are using for measurement-based quantum computing. Because now I can continue with this. And actually, if I do it with a big enough cluster state, I can implement any single qubit rotation. And again, it's just I need to update these measurement bases. You can also do a 2-qubit synod. I'm not going to go through that explicitly, but basically with you have 2 input qubits like that, you can make a synod between them by measuring in correct basis on such a cluster here. Okay, so one question. Well, maybe okay. So that's enough. And then the question is basically, how do you do universal quantum computing? You need to make sure that your cluster is big enough. So you can think of it as basically each of these kind of qubit lines here. That's your input qubits. So that's basically the width of your computation, how many qubits are measuring on. And the length of this is your depth of computation, right? Because as I measure it out, I'm applying a gate, then I need to measure more to apply another gate. And that way that gets basically my circuit depth. And there are different ways to make such a cluster state that you can do universal computation on. You can have just a grid like this. Forget about fault tolerance right now. You can do a brick layer. There are different topologies, and you can basically choose which ones are best to do your computation depending on, for example, resources. Do you want to minimize the number of qubits they need and whatnot? One question, do I need this cluster state to be live fully before I start my computation? So do I need to do all these entangled measurements first and then do the measurement? Yep.
No. As we described also.
That's right. It doesn't matter that, I mean, I just need to make sure that I can entangle qubits fast enough as I measure them so I can continue my computation. I don't need to first entangle them and then do the measurements, right? Because as I've entangled 2 qubits, if I do a measurement on that one, it's not going to change anything on this one, basically, right? Only when I do the measurement on there, I continue the computation. Okay, so that's basically the basic of measurement-based quantum computation. And that's very nice to understand how you do blind quantum computation, because step 1 is then just take a server, it prepares this blind quantum computation resource, doesn't have to apply it all in one, can do it as a function of time. You just send each qubit to the client measures them, adapts their measurement basis based on the outcomes, and implements basically the circuit that they want to do. All right, so why is this blind? That's right. There's no flow of information back to the server, right? There's only flow of information from the server to the client. So the server knows nothing about what the client does. And it would be, I mean, because we're really just sending qubits here, it doesn't matter the entangled stuff that is in the queue at the server side, right? Because information has to flow back in order to be any kind of learning from the computing side for the client. So by doing this, we can ensure that they don't know anything about what they're doing. Right, so we ensure this, but we actually do leak some information. Right, because we do need to ask the server to prepare a certain state, how many qubits do we want in that state, how long a computation are we going to run. That leaks information. It leaks information about the depth of the computation that we're running, and leaks information about the width of the computation we're running. Do we leak more information than that? Oops. I would argue yes, because we're also got kind of circuit structure that is in this graph. Maybe we say, okay, we just prepare a brick layer that comes with a certain width and a certain depth. Well, there's not also all connectivity in a brick layer, right? If I want to do a gate between the qubit that's up there and the qubit that's down here, I need to basically measure out a pattern and use up a large part of my depth of my computation to do a gate between these. So if the server knows, well, this is the size of the cluster, this is the width of the cluster, and it's a brick layer, it's not like I could implement any unitary on that brick layer. I'm also limited by the structure of the resource state that I have. So I'm also leaking that kind of information. So it's just basically to exemplify that when people say blind quantum computing, you don't learn anything, you do learn something. And it's not just the depth of the computation and width of the computation, you also learn something about the structure of computation from the choice of graph that this computer designs. So it's more about sensitive information. Right? We just need to make sure that we specify in blind quantum computing what is the information that you don't want to learn. That's what one can hidden. We will always leak some information, but maybe we don't care about the width and the depth and the structure. There's something else that we care about. Okay, now for practical blind computing, we kind of need to keep some other things in mind. One is it's costly to transmit quantum information over a network, I would argue, right? So it's going to be a costly thing to do. It needs to be loss tolerant. Well, we know how to do that with a quantum network. Maybe we need to kind of pre-distributed entanglement, the teleportation is a way to do it, but that's something that we keep in mind. So just to keep in mind, when I say we just send a qubit, it's not, most likely we're not just going to send a photon or something like that, because then if we lose that photon, it's going to be a very inefficient computation. So we need some sort of pre-distributed entanglement, I think, to make this practical. Another thing is, if we take a step further up and say, well, actually, any kind of useful quantum computation, most likely you want error correction on it, it becomes even more costly, because as we know, when we put quantum error correction on, some operations that were quite easy to do physically, like some rotations and qubit rotations, become kind of hard to do. Non-Clifford operations are hard, well, depending on the choice of code, but I mean, different non-Clifford operations are hard, but there will always be one that is hard. And if we want to hide from the server, at what point in the circuit do we do non-Clifford operations, for example? Well, then naively, we need to make sure that in principle, we could do it on any part of the circuit. Right? So that means that if we're talking about, well, we're very much after these efficient quantum algorithms where the number of Clifford states maybe is, logarithmic in size or something like that, because we know it's costly, so we want to have something that runs efficiently on a quantum computer. Well, if you really want to do it completely blind, you can just throw that out, right? Because then everything will just scale with the width of the depth of computation, because you should make sure the server doesn't know anything about where you're doing the non-Clifford. So that's also a very costly thing about blind quantum computing, the ones to keep in mind. Because it costs a lot to distill magic states, for example. All right. So when we design basically a blind quantum computing system, we should really think carefully about what information is necessary to hide. Am I okay with the server learning something about where I do some non-Clifford gates, for example, right? Am I okay with it learning about something about the structure? Because anything I can kind of relax on those, I would argue makes it cheaper to do blind quantum computing. And if I was a service provider, I would say if you need 1,000 magic states, that's going to cost you a lot. If you do 2, it's going to be faster and it's not going to cost you that much. So I think for practical implementations, these things will definitely matter. And that's something that we should really think about. when designing these things. All right. And now I'll basically switch a little bit from a lecture to a more research talk about some recent work that's been done at Harvard about these blind quantum computing circuits, and especially addressing these questions that I've raised here. Okay, so let me, before I do that, are there any questions? Yeah.
Two-dimensional cluster.
Sorry?
How to create a two-dimensional cluster? Connect the qubits to the, how do you do that?
How you do it?
Yeah.
Well, you just need to do gates between the qubits, right? And you can fold it in different dimensions.
Yeah, some of those like edges are missing, so the qubits are not entangled. Like you say, create two linear clusters and only entangle these two qubits. How do you do that? Without entangling each pair.
Yeah. Well, it's good. I mean, it depends on your connectivity of your hardware, right? I mean, can you do gates between only neighboring qubits? Can you do gates between all to all? Some hardware platforms have all to all. Some people have connectivity, and that will determine which cluster states are most efficient for you to prepare, which probably will inform, indeed, whether it will do the 2D grid, will do some other kind of clusters that you do. If you look at another thing you can do is you can always redesign your cluster. So basically, if I have a cluster that looks like this, I can do a C measurement here on that qubit, and that basically just prepares this cluster. So I can also reshape a cluster that I made first into other shapes by doing measurements on qubits in between. I can also, by measuring in different bases, make connections between these. So you can, by doing measurements, also reshape your cluster from a certain fixed starting point to another point, if that's what you want. But you're exactly right that, I mean, things like connectivity of your hardware and all comes into play. We'll do. All right. So let me get this out of the way and go here instead. And okay. So change of pace. I'm not going to ask you to do calculations in this part of the talk. It will be more research-based. So this is really trying to focus on this point of, okay, how do we make it less costly to do the BQC when we actually want to implement it in practice? And there's some things that we can use here. One is, well, we'll have a very powerful quantum computer, right? It can run fault-tolerant quantum operations, meaning that it has low gate errors, has fast computation speeds, and it can also operate as a circuit-based quantum computer, right? So naturally, in many of these applications, I mean, photonic quantum computing is a bit different. They're really about measurement-based, right? But for many of the hardware, it's not really measurement-based that you're kind of thinking of. It's more circuit-based, even though there's, of course, a one-to-one mapping between the two. The other thing is that the network, that will be lossy. It will need photonic connections. It will be costly, and it will be slower than our local operations, right? We have a distance element here. We're going to be far away. We definitely need to transmit information, so it's not just nearest neighbor as what we had in the quantum computer. So how can we design a very efficient blind quantum computing protocol here? One is, okay, let's embrace the fact that this is a circuit-based quantum computer. So how do we do the blind gates in such an architecture? Right? How do I do the mapping from the measurement-based into just kind of a circuit-based thing? The other thing is, as I talked about, well, you know, if I require everything to be blind, it's going to be super costly. If I have a certain application in mind, can I maybe do some things, some clever circuit design such that I can lower the cost, lower the number of blind gates that I need to do while still keeping the information that I care about hidden? And the final thing is, let's not forget about fault-tolerant operation, right? How do I ensure that I can do the quantum error correction efficiently and lower the cost that I need for implementing it? So let's start with the first one. I can do teleportation to do blind gates, right? So if I take and entangle with a qubit a photon and send that photon to my client, and the client measures the photon in a basis like this, just as we looked at before, well, then I'm going to implement a blind C rotation on the qubit left at the server. And I said before, the gate that we looked at, this W of omega, that's basically just a Hadamard and a blind C rotation. Okay, so now I know how to implement that gate up to a Pauli correction, basically. And how can you entangle a photon with your spin? Well, you could use some of the gates that we discussed yesterday, for example, the phase-based gate. Maybe that's how you want to do it. All right, it's completely blind, right? Because there's no information flowing back. If the server looks at their qubit, they won't be able to tell what kind of rotation you did. It'll be a completely defaced thing. All right, but if I do it like this, where this is part of the computation, I'm still not really loss tolerant, right? Because if I lose the photon, well, then that qubit is kind of decoherent completely, and that would be a problem if it's a valuable qubit part of my computation. So we need to make it loss tolerant. So we need some sort of auxiliary qubit that we can try and make this kind of blind rotation on. And every time we fail, we try again. That means that there will be now, remember I said to begin with, there was only flow information in one direction from the server to the client. When I want to make it loss tolerant, there kind of want to be, there needs to be some information flowing back, right? Did I receive the qubit? And do you now continue with the computation or not? So just I mean, it's not a problem, but just a word of warning, want to make sure that that information that flows back, we cannot just rely on the fact that no information flows back, therefore it's secure. We want to make sure that that information that flows back doesn't leak any information about your computation, which it kind of intuitively shouldn't, because the information I'm just saying is, yes, I received the photon. There's no information about what measurement basis I chose or anything like that. So I can ensure still that this is blind. So the idea is I try this until I'm successful, right? And once I'm successful, I tell the server, okay, now I did the, what I wanted to do with that qubit, teleport it into the computation. And you can basically do this, and when the server does the teleportation into the computational qubit, there will also be a correction. Because when we do the computation, maybe I wanted to implement rotation theta, but I might also, in the teleportation, have implemented minus theta rotation, which is not what I wanted. So what do I do? If I get, the server sends me the measurement outcome, M of that computation, and depending on that, I can do another one. If it rotated in the wrong direction, I try again with 2 theta. If I'm successful, I'm happy. If I'm unsuccessful, all right, then I need to try with minus 3 theta, and so on. Right? So I can try until I get the right rotation. And it's a 50-50 chance. On average, I only need 2 tries to do it. But you can also ensure that it's deterministic, basically. If you have a theta that you now say, well, it's just some kind of fraction of 2 pi, then I can ensure that within a certain time, a certain number of attempts, I will have done this. So why is that? I guess it's a question to you guys.
This orange one is the blind qubit?
The red one is the computational qubit. So basically, look up here, you have the computational qubit there, which is part of your computation.
Which is in the server.
Which at the server. The auxiliary qubit, or the communication qubit, also at the server. The orange qubit, that's a photon that I send to my client to measure.
Oh.
So the question here is, why is it that I can say that if my phase here is some fraction of 2 pi, I will always succeed within a limited number of attempts? So remember what happens, I try to rotate it theta. If I fail, I'm going to rotate it the other way. And I try to rotate it back. If I fail, I rotate it the other way. Why does that ensure then that at some point I will always succeed?
2 power C is the
No, this is just how many choices of theta do I have, basically. So I'm saying here that, okay, for the computation, I might not need to measure every thetas, right? I might have a set of thetas that I want to implement. And if I have such a finite set, like this, I can ensure that, I mean, even though we say it's actually kind of efficient, right? On average, I only need 2 attempts that I succeed, but I still have the small probability that I need many attempts to succeed, which is a little bit annoying. But I can ensure that you have a finite number of attempts, and then you for sure will have succeeded within that. And the question I'm asking is, why can I make that statement? Exactly, yeah. If I continue to fail, I'm basically just gonna go around, and at some point I'm gonna hit the one that I wanted. So there's a limited number of failed attempts, and at some point I actually will succeed. Yep.
It's like a run wall. You can just be going back and forth, right?
No, because every time I update the theta that I'm doing, right? If I failed, I'm going to try and attempt with the theta that rotates all the way the other way. So it's not the same measurement I'm doing.
But how would the customer know that he succeeded?
The customer gets the measurement outcome M from the server.
And you begin an ending basis.
So the customer measures in the basis. That implements this blind rotation on the communication qubit. Then the server makes a bell measurement locally to teleport that qubit into the computational qubit. During that bell measurement, that's where it can, in principle, go wrong, in the sense that depending on the measurement outcome of that bell measurement, I'm either going to rotate the right or in the opposite direction. But that's determined by the measurement outcome M.
So do we know what output we want?
Yes, I know what M I want. If M is 0, I'm done. If M is 1, I need to try again. So the server gives me that information of M, and I can use that to make sure that I implement what I want. Okay. So in this way, I now actually have what I need to do blind quantum computing. I can do, just as we did before, I mean, if I can do this blind C rotation, I can do a Hadamard afterwards, it's done. And actually, I don't need to make the Hadamard blind. The server can do the Hadamard. Whether I do a single qubit rotation or not, it's completely hidden in what I do for these blind C rotations. Right, so maybe I choose these thetas to be such that I'm doing nothing. 2 Hadamard does nothing, I did identity. Server doesn't know whether I'm doing something to the qubit or not. I'm hiding that information. Okay, single qubit only gives me part of the thing that I need. I also need to do an entangling gate. I see not. Well, I can do it in this way. I can actually ask the server to, it does an entangling gate here. Then I do this blind rotation and another entangling gate. So again, these are not blind. The server knows that it's doing this, but whether I'm actually doing entangling gate or not is hidden in that one, right? Because depending on my choice of this theta, these are just going to map out to identity or an entangling gate. So now I have the toolset that I need to do blind quantum computing. And all I need is this blind C rotation. Okay. Yeah, it's very important also that these are Clifford gates, basically, which means that it will just change the Pauli frame, as we said before, that I just need to keep track of what is my qubit, 0 and 1, and the phase of those things. And that's sufficiently, I can keep that with the client. I don't need to feed information about these things into the server. All right, so we have our loss tolerant implementation of these blind gates. We have a universal set. We can do it on these circuit-based. I don't need them to change their computation way to do like these cluster states and whatnot. Just keep doing what you're doing. We just need this kind of network interface. So I still need to lower the cost. I still have all these other costs that, well, do I want to do every gate blind? Do I need to do a lot of non-Clifford gates to do this? We still need to talk about that. So these are the remaining 2 elements, circuit designs and efficient fault-tolerant operation. So start with that one. Okay, so there was like this bricklayer state that I showed before. And you can do a bricklayer circuit, kind of like the same structure here, right? We know how we do the single qubit gates, we know how to do the 2 qubit gates. But every time we do it, so for a single qubit gate, we need 3 blind gates, which means that we need 3 network connections to the client. Every time we do a 2 qubit, we need 1 blind gate, so we need 1 network connection. So if I really want to keep everything blind, it's still very costly. All right, we're still in this situation. Okay, can I make some of these things known to the server? Not keep everything blind. Can I keep something, make something known and say, okay, you're allowed to know these circuits, and in the same way, still kind of rigorously, I still need to be very careful to say, I want to make sure that this information I care about is not leaked. And of course, it depends on what you want to do, which things you can make blind, which things you cannot. So it's not like here that I'm going to give you a universal recipe for how you can do that. It very much depends on what application you're running, what are the things you want to keep safe. So it's more, I'll give you a little bit of a start to think about this thing, give you some examples of where you might be able to save. And then it's a more kind of, indeed, I'm just kind of saying, when you go out and try to design these, keep this in mind. Can you make these more efficient? Keeping information hidden. So one example of this that I'm going to highlight is Hamiltonian simulation, because, well, that's one of the things that we probably want to do with quantum computers, at least it looks like now. So, okay, such Hamiltonian simulation, I can implement, these multi-qubit Pauli rotations to simulate my Hamiltonian, and want to do that fully blind. It would need me to do something like this circuit here, completely blind. So that hides basically that I'm doing Hamiltonian simulation altogether. It's just completely hiding the information of what I'm doing. Could also be doing something else. But maybe I'm okay with the computer knowing that I'm doing Hamiltonian simulation. Because to be fair, how many other things could I be doing with the quantum computer, right? Maybe what I care about is actually not the server to know which Hamiltonian I'm simulating and the outcome of that simulation. It's a new drug I'm developing. It's okay that it knows that I'm doing simulation. It's just I don't want it to know which Hamiltonian I'm simulating. I don't want it to have the recipe for my new drug. All right. Okay, so how could I do that? Well, this is the place where I'm saying which Pauli angle, what is the angle that I'm doing this rotation around, right? And that kind of is a little bit what keeps the information about what Hamiltonian I'm doing. Of course, also which Pauli string that I'm doing, but in principle you can say, well, I could do it between all Pauli strings, and then I just either choose to not do a rotation, choosing this theta to be 0, or choose it to be something. So by just keeping this theta hidden, I can kind of hide what Hamiltonian I'm doing. The server might know from this circuit that, oh, this guy is doing like multi-qubit Pauli rotations. Most likely he's doing Hamiltonian simulation, but they don't know what I'm simulating. And there's a big win here, because here I need all these gates to be blind, right? These are, 3 blind gates per single qubit gate, 1 per entangling. Here I just need 1 blind gate. So while before, that number of blind gates would actually scale polynomially with the number of qubits that I have in my Pauli rotation, it's constant now, just 1. So that can give me a kind of significant saving. As again, this is not just an example. So it's not something you can go in and say, okay, this, in general, you can apply this. You need to carefully think about what you're going to do, what you want to keep hidden. But another tool that you might be able to use to guide you there is something called the expressibility, which is a little bit the measure for the ability of a circuit to be able to sample in the space of possible unitaries that you can do. So you can say, okay, if I have a low expressibility, my blind circuit can implement some unitaries, but they're very similar. If I have high expressibility, my blind circuit can implement unitaries that are kind of quite different. High expressibility, I can do many different things on it. So that's something that you might be able to use to guide you a little bit in terms of how to design my blind and non-blind parts of the circuit. And as an example, if you just do this blind rotation here, with just a single qubit, and compare it to a bricklayer, you can kind of ask the question, what is the depth of the circuit I need to do with the bricklayer to get the same expressibility measured as if I did it with blind rotations? And there were done some simulations here where basically this is the number of blind gates in the bricklayer circuit that you need in order to get the same measure of expressibility as if you do a circuit with different n-qubit Pauli rotations. Well, of course, in there, I'm saying explicitly the same measure of expressibility because it's not, I'm not saying that it's necessarily the same unitaries that you can sample. Right? So expressibility is just kind of a measure for how different unitaries can you measure, but it's not when I say that these hit the same measure of expressibility, it's not the same as saying that you can do the same things with these two. It's just that, you know, the size of things you can do is kind of the same. And what you can see is that you can, by choosing how you decompose your circuit, how you compile it, do you do it with the power rotation, do you do it with big layer, you can have very different numbers in terms to get the same expressibility. And so again, this is not something you can just go and apply, but it's something that, you know, keep this in mind when you're deploying this, that how you choose to decompose your circuit can matter a lot for your resources. Okay. All right.
How do you communicate this theta which is hidden? Usually, like it's not adding security, it's like more of privacy preserving and communication. So if you communicate this theta to a classical means or to some quantum means?
Well, the theta, you don't communicate the theta to the server, right?
It's hidden, so the client has to communicate it with the server.
No, I mean, the theta never is communicated. That would destroy, I mean, then it would be known to the server what I'm doing. Yes, so this is your measurement basis that you choose to measure. I mean, what we went through before, that you choose measure your photon in a certain basis. That basis choice, that's where theta comes in, right? Whether measured in 0 plus e to the I theta 1 plus minus, yeah.
Yeah. So this basis is selected by the client.
Yes.
During the computation, or
yeah. So as we saw in the beginning, right? When you do this measurement, you need to update your choice of theta to make sure that you're doing the right things. Same thing you're doing here. What we talked about was that if the bell measurement is, for example, wrong, you need to update your theta to get the right one. And then depending on how you decompose your circuit, you just choose the thetas that you want to do the power rotations. Okay. So now we talked a little bit about how you do blind gates in this hybrid architecture, right? We also talked about, well, depending on what you're doing, you might want to think carefully, maybe it's because I'm hitting this one, about how you compile your circuit, which kind of blind element you want to use. And then the final element we'll get to now is then, okay, let's think about fault tolerant operation. It's the final thing, right? What is it that we can maybe learn from that? Yeah. Okay. So, sorry about the light sync logo here. That's left over because I reused some slides. So error correction is actually not an interesting thing to hide. Right? I mean, if it's fully blind, I would actually not want the server to know that I'm doing error correction. But who cares? We know that you need quantum error correction to do things efficiently. I'm okay with the server knowing that I'm doing quantum error correction, right? So why would I need to hide that? I don't need to do blind stabilizer measurements and send the result to me. I mean, I'm okay with the server doing that. It's not really saying anything about what I'm calculating. Okay, so I don't mind. Because exactly, I mean, the fact that I'm doing error correction is not saying something about the application that I'm running. All right. Also, we really want to keep the error correction at the server side. If you have like a matter-based quantum computer, that's efficient at doing error correction. So we want those to just do all stabilizer measurement locally. I don't want to connect this to a network that's lossy such that I get bad stabilizer measurements, right? So can I in some way just do everything locally, no blind fashion, and then in that way have a better performance for combinatorial code. Okay, so where do you start is that you choose a certain quantum architecture code that you want to use. You know, could be whatever, based on your hardware. Do you want to do QLDPC codes if you have good alternate connectivity? Do you want to do surface code if you have limited connectivity and whatnot? You construct your logical gate set. Right, depends on the code. Which things do you need to do with magic states, for example? Which things can you do with Clifford gates? And what I really have here is if there's something where I can do transversal operation, that's very suited for this. So basically, in surface codes, for example, I can do these things transversally. I can have a set of transversal gates for doing teleportation, right? To input magic states into my computation, and I have transversal operations of Clifford gates that I need to my computation. And that's nice because now I know how to implement these gates blindly as well. Because if I want to implement a transversal gate blindly, I just need to do this single qubit blind rotations on all qubits in the logical qubit, right? And then I've implemented the gate, the logical blind gate. Right, so if I can implement a logical blind rotation, C rotation transversally, I know how to do it with just my physical blind gate that I showed before. I just do it for all the qubits. Okay. And luckily we do have codes that can do that. And some of them are very good, surface code, for example. Okay. All right, so now I know how to implement my blind logical gates by using these transversal operations. And then the next thing is, we should then think carefully about which things do I want to make known to the server, which things do I not want to make known. Can I limit the number of magic state installation that this server needs to do to basically reduce the cost of the computation? All right. Just to time out again, so if I have these efficient transversal gates, I do my blind rotation, just as printed here. I have all these qubits, part of my logical state. I do just single blind qubit rotations, as I showed before, and I get that on a blind level. To do entangling, transversal entangling gates, again, I know how to do that physically, so I just implement that, and I have a logical entangling gates between these. And I can use that to input magic states that are distilled at the server. So the server can keep their magic state distillation factory, they can distill these things, and then basically using my blind interpretation, they can come with one of their magic states. I can choose whether I'm going to input it or not, because this is a blind entangling, right? So maybe I entangle it, maybe I don't. If I entangle it, I'm going to input magic. If I don't entangle it, then I'm not going to input magic. So I can hide the fact whether I'm doing these non-Clifford gates or not. What about doing stabilizer checks? I want to do that at the server, basically. So at this logical level, the server can just take their auxiliary qubits, do the stabilizers, measurement stabilizer checks, and send the information to me and as a client. And then me as a client will do the symptom checks, basically, and figure out, did an error happen and whatnot. So the whole quantum error correction, the stabilizer measurements are being performed at the server. The decoding is happening with the client. That's nice because now I can do efficient stabilizer measurements locally, and I'm not hit by the fact that I have this networking error. So looking a little bit at what that gives you, we've done some simulations of basically random quantum circuits. So you just plug in random single qubit, 2 qubit gates, and you make some of them blind, and you make some of them not blind. So again, here I'm not looking at a specific application. I'm saying, okay, how does actually the quantum error correction capabilities or the quantum error correction performance change when I do different fractions of blind gates? As you might intuitively predict, well, if I want a certain logical error and I do less, if I have faulty network connections, the less blind gates I do, the better logical error I'll have at the end. Right? If I only do one blind gate, I can have a pretty high error. If I do 1,000, I need to have a really low error of these things. That's one thing, of course. The other thing is also you can ask, what is the logical threshold to ensure that you basically can correct your errors? And how does that change as you do more or less of these blind operations? And this is a little bit what is shown here. So this is where you assume a certain local error rate of the gates at the server. So these are the gates that are being used to stabilize measurements and non-blind gates. And you have a certain error rate for blind gates, which is higher. And naturally, if everything is being done at the client side, meaning that also stabilizer measurements are being done at the client side, there's not really any difference between these two. Right? I need very low error rates also on my networking, comparable to what I have on my logical error on my computer. That's a little bit, right? So we're never really talking about when we need quantum networking that we need to be, down at 10 to the minus 3 error or something like that as we want to do computation. Okay, if I offload the stabilizer measurements to the local computer, I want to do a lot better because now I have very efficient and low error stabilizer measurements. So I'm good at catching where these errors are. So I can tolerate more error when I do my blind gates. I'm still doing everything, the whole gate's blind, but I'm doing the stabilizer measurements now locally in a non-blind fashion. So now the server knows that I'm doing quantum error correction, but that's it. Doesn't know anything else. And then I can start to make some of them known, some of these gates that are in my computation. And of course, the more that I make known, the less I'm doing, and my threshold increases. It can be about an order of magnitude higher than what I have if I did everything blind. All right, so it relaxes the requirements on my networking interface to do these BQC things. All right. So in summary, tapping a bit into how to do practical blind quantum computing. One is, well, maybe you want to actually leverage the fact that they're doing circuit-based quantum computing and not measurement-based. But there is a mapping between the two, so it's just this blind C rotation that needs to be able to do. It all works over. Second is start to think about what is actually the information you want to keep hidden. And once you've come to a conclusion there, you need to think about how you then compile the most efficient circuit to minimize basically the requirements on the networking and the number of non-clifford gates that you want to do to keep it blind. Otherwise, as we talked about, it will be super expensive, both to have a very, very efficient networking interface that's really below the threshold of these quantum error correction codes, and in terms of magic states that the server needs to do. And finally, indeed, I think to me it's pretty clear that we're not going to care about whether the server knows we're doing quantum error correction. Just offload as much as that as you can to the server right away. It helps you. All right. I should say this work here is work from all these people here, and Aria is in here as well. And I think if you have more questions about these things or follow-up things, I think Aria is the one to talk to, so you should definitely go and ask her. There's both the theoretical work, which is what I've been talking about today. There's also a nice kind of experimental implementation that I want to point to, and the reason is that this experimental implementation is using the scattering-based gates that we discussed yesterday to exactly do this. You entangle spin with a photon, you measure on different bases, and that way you implement the blind thing. Showing how this hopefully fits together. All right. With that, I'll end this part of the lecture and ask if there are any questions. Not lecture, this was more a research talk, right? All right. Then let's stop 5 minutes early for lecture. And when we get back for the next lecture, it's also going to be a little bit researchy, but it's going to be much higher level, and it's going to be about quantum sensing, basically, network sensing. All right, thanks.